What if I told you the key to unlocking the deepest secrets of the universe was almost lost? That humanity's greatest eye on the cosmos, the James Webb Space Telescope, was born from a series of near-impossible challenges and decades of relentless determination? Today, we're diving deep into the story behind this unprecedented marvel, exploring how it captures the raw data that's transforming our understanding of the universe, and why it might just be the most important scientific instrument of our time. Who is James Webb? James Webb, born October 7, 1906, Tally Ho, North Carolina, U.S., died March 27, 1992, Washington, D.C., was an American public servant and administrator of the National Aeronautics and Space Administration, NASA, during the Apollo program, 1961–68. What is JWST? The James Webb Space Telescope is the largest, most powerful space telescope ever built. It will allow scientists to look at what our universe was like about 200 million years after the Big Bang. The telescope will be able to capture images of some of the first galaxies ever formed. It will also be able to observe objects in our solar system from Mars outward, look inside dust clouds to see where new stars and planets are forming, and examine the atmospheres of planets orbiting other stars. Why was the JWST launched? The James Webb Space Telescope is a giant leap forward in our quest to understand the universe and our origins. Webb is examining every phase of cosmic history, from the first luminous glows after the Big Bang to the formation of galaxies, stars, and planets to the evolution of our own solar system. Timeline or launched. On December 25, 2021, and 7:20 a.m. Eastern Time, 12:20 Universal Time Coordinated, the James Webb Space Telescope was launched by an Arianespace Ariane 5 rocket from Europe Spaceport in French Guiana. The rocket and launch site were part of the European Space Agency's contribution to the mission. James Webb Space Telescope. The James Webb Space Telescope, JWST, is a space telescope designed to conduct infrared astronomy. As the largest telescope in space, it is equipped with high-resolution and high-sensitivity instruments, allowing it to view objects too old, distant, or faint for the Hubble Space Telescope. 9. This enables investigations across many fields of astronomy and cosmology, such as observation of the first stars and the formation of the first galaxies, and detailed atmospheric characterization of potentially habitable exoplanets. 10. Features. The mass of the James Webb Space Telescope, JWST, is about half that of the Hubble Space Telescope. Webb has a 6.5 m, 21 feet, diameter gold-coated beryllium primary mirror made up of 18 separate hexagonal mirrors. The mirror has a polished area of 26.3 square meters, 283 square feet, of which 0.9 square meters, 9.7 square feet, is obscured by the secondary support struts, 15, giving a total collecting area of 25.4 square meters, 273 square feet. This is over 6 times larger than the collecting area of Hubble's 2.4 meters, 7.9 feet, diameter mirror, which has a collecting area of 4.0 square meters, 43 square feet. The mirror has a gold coating to provide infrared reflectivity, and this is covered by a thin layer of glass for durability. 16. Webb is designed primarily for near-infrared astronomy, but can also see orange and red visible light, as well as the mid-infrared region, depending on the instrument being used. 10-11. It can detect objects up to 100 times fainter than Hubble can, and objects much earlier in the history of the universe, back to redshift Z is almost equal to 20, about 180 million years cosmic time after the Big Bang. 17. For comparison, the earliest stars are thought to have formed between Z is almost equal to 30 and Z is almost equal to 20, 100 to 180 million years. Cosmic time, 18. And the first galaxies may have formed around redshift Z is almost equal to 15, about 270 million years cosmic time. Mission goals. The James Webb Space Telescope has 4 key goals: to search for light from the first stars and galaxies that formed in the universe after the Big Bang, to study galaxy formation and evolution, to understand star formation and planet formation, to study planetary systems and the origins of life. Infrared astronomy. Webb is the formal successor to the Hubble Space Telescope, HST, and since its primary emphasis is on infrared astronomy, it is also a successor to the Spitzer Space Telescope. Webb will far surpass both those telescopes, being able to see many more much older stars and galaxies. Observing in the infrared spectrum is a key technique for achieving this because of cosmological redshift and because it better penetrates obscuring dust and gas. This allows observation of dimmer, cooler objects. Since water vapor and carbon dioxide in the Earth's atmosphere strongly absorbs most infrared, ground-based infrared astronomy is limited to narrow wavelength ranges where the atmosphere absorbs less strongly. Additionally, the atmosphere itself radiates in the infrared spectrum, often overwhelming light from the object being observed. This makes a space telescope preferable for infrared observation. Scientific results. The JWST completed its commissioning and was ready to begin full scientific operations on July 11, 2022. With some exceptions, most experiment data is kept private for 1 year for the exclusive use of scientists running that particular experiment, and then the raw data will be released to the public. JWST observations substantially advanced understanding of exoplanets, the first billion years of the universe, 260, and many other astrophysical and cosmological phenomena. Location and orbit. Webb operates in a halo orbit, circling around a point in space known as the Sun, Earth L2 Lagrange point, approximately 1,500,000 kilometers, 930,000 miles, beyond Earth's orbit around the Sun. Its actual position varies between about 250,000 and 832,000 kilometers, 155,000 to 517,000 miles, from L2 as it orbits, keeping it out of both Earth and Moon's shadow. By way of comparison, Hubble orbits 550 kilometers, 340 miles, above Earth's surface, and the Moon is roughly 400,000 kilometers, 250,000 miles, from Earth. Objects near this Sun-Earth L2 point can orbit the Sun in synchrony with the Earth, allowing the telescope to remain at a roughly constant distance with continuous orientation of its sunshield and equipment bus toward the Sun, Earth, and Moon. Background: development to 2003. Discussions of a Hubble follow-on started in the 1980s, but serious planning began in the early 1990s. The High-Z telescope concept was developed between 1989 and 1994. A fully baffled B 4 meters, 13 feet, aperture infrared telescope that would recede to an orbit at 3 astronomical unit (AU). This distant orbit would have benefited from reduced light noise from zodiacal dust. Other early plans called for a Nexus precursor telescope mission, correcting the flawed optics of the Hubble Space Telescope, HST, in its first years played a significant role in the birth of Webb. In 1993, NASA conducted STS-61, the space shuttle mission that replaced HST's camera and installed a retrofit for its imaging spectrograph to compensate for the spherical aberration in its primary mirror. The HST and Beyond Committee was formed in 1994 to study possible missions and programs for optical ultraviolet astronomy in space for the first decades of the 21st century. 81. Emboldened by HST's success, its 1996 report explored the concept of a larger and much colder, infrared-sensitive telescope that could reach back in cosmic time to the birth of the first galaxies. This high-priority science goal was beyond the HST's capability because, as a warm telescope, it is blinded by infrared emission from its own optical system. In addition to recommendations to extend the HST mission to 2005 and to develop technologies for finding planets around other stars, NASA embraced the chief recommendation of HST and beyond for a large, cold space telescope, radiatively cooled far below 0 degrees Celsius, and began the planning process for the future Webb telescope. Preparation for the 2000 Astronomy and Astrophysics Decadal Survey, a literature review produced by the United States National Research Council that includes identifying research priorities and making recommendations for the upcoming decade, included further development of the scientific program for what became known as the Next Generation Space Telescope, and advancements in relevant technologies by NASA. As it matured, studying the birth of galaxies in the young universe, and searching for planets around other stars, the prime goals coalesced as Origins by HST and beyond became prominent. As hoped, the NGST received the highest ranking in the 2000 Decadal Survey. An administrator of NASA, Dan Golden, coined the phrase faster, better, cheaper, and opted for the next big paradigm shift for astronomy, namely, breaking the barrier of a single mirror. That meant going from eliminate moving parts to learn to live with moving parts, i.e. segmented optics. With the goal to reduce mass density tenfold, silicon carbide with a very thin layer of glass on top was first looked at, but beryllium was selected at the end. The mid-1990s era of faster, better, cheaper produced the NGST concept, with an 8 meters, 26 feet, aperture to be flown to L2, roughly estimated to cost $500 million. In 1997, NASA worked with the Goddard Space Flight Center, Ball Aerospace and Technologies, and TRW-88 to conduct technical requirement and cost studies of the 3 different concepts, and in 1999 selected Lockheed Martin and TRW for preliminary concept studies. Launch was at that time planned for 2007, but the launch date was pushed back many times. See table further down. In 2002, the project was renamed after NASA's second administrator, 1961 to 1968, James E. Webb, 1906 to 1992. Webb led the agency during the Apollo program and established scientific research as a core NASA activity. In 2003, NASA awarded TRW the $824.8 million prime contract for Webb. The design called for a D-scoped 6.1 meters, 20 feet, primary mirror and a launch date of 2010. 93, later that year, TRW was acquired by Northrop Grumman in a hostile bid and became Northrop Grumman Space Technology. Early development and replanning, 2003 to 2007. Development was managed by NASA's Goddard Space Flight Center in Greenbelt, Maryland, with John C. Mather as its project scientist. The primary contractor was Northrop Grumman Aerospace Systems, responsible for developing and building the spacecraft element, which included the satellite bus, sunshield, deployable tower assembly, DTA, which connects the optical telescope element to the spacecraft bus, and the mid-boom assembly, MBA, which helps to deploy the large sunshields on orbit, 94. While Ball Aerospace and Technologies was subcontracted to develop and build the OTE itself, and the Integrated Science Instrument Module, ISIM. Cost growth revealed in spring 2005 led to an August 2005 replanning. The primary technical outcomes of the replanning were significant changes in the integration and test plans, a 22-month launch delay, from 2011 to 2013, and elimination of system-level testing for observatory modes at wavelengths shorter than 1.7 micrometers. Other major features of the observatory were unchanged. Following the replanning, the project was independently reviewed in April 2006. Detailed design and construction, 2007 to 2021. In January 2007, 9 of the 10 technology development items in the project successfully passed a non-advocate review. These technologies were deemed sufficiently mature to retire significant risks in the project. The remaining technology development item, the MIRI cryocooler, completed its technology maturation milestone in April 2007. This technology review represented the beginning step in the process that ultimately moved the project into its detailed design phase, Phase C. By May 2007, costs were still on target. In March 2008, the project successfully completed its preliminary design review, PDR. In April 2008, the project passed the non-advocate review. Other past reviews include the Integrated Science Instrument Module Review in March 2009, the Optical Telescope Element Review completed in October 2009, and the Sunshield Review completed in January 2010. James Webb Interviews. Interviewer: if you could deliver a message to the scientists and engineers working on the JWST today, what would you say? James Webb: I would say this. You are the pioneers of our time. You are pushing human knowledge further than it has ever gone. What you're doing is for the entire human race, and your work will be remembered for centuries. Keep asking the hard questions, keep. One of the top priorities for NASA with the JWST is the study of exoplanets, planets outside our solar system. Webb's powerful instruments are being used to analyze the atmospheres of these planets, searching for chemical signatures such as water vapor, methane, carbon dioxide, and other indicators of potential life. NASA is focusing on planets in the habitable zone, where liquid water could exist, which could increase the chances of finding life. As the James Webb Space Telescope, JWST, drifts through the vast darkness of space, it is silently gathering secrets from the very edge of time. Each discovery peels back layers of the universe's hidden story, a story billions of years in the making. But the greatest questions remain unanswered. Could this telescope unlock the mysteries of our cosmic origins? Could it lead us to life beyond our world? The answers lie in the data it collects, waiting to rewrite the very foundations of what we know about existence. The journey has just begun. Stay with us as we explore the uncharted territories of space with the James Webb Space Telescope, and see what mysteries await on the horizon. Subscribe and keep watching as we unravel the universe, one discovery at a time.